Good morning, good afternoon, good evening guys, girls and gentlebods, and welcome back to the shed. In this episode I'm going to be continuing with work on the cylinder head. So I'll reposition the camera and you can see what we're doing. There's all the valves. They've got to go down to the workshop to be decoked. I'll put them in the lathe and clean them nicely. So I'll put that out of the way and move this along a bit. Get it in some better light, and the first thing I'm going to do is just get rid of some of the carbon out of the combustion chambers and ports. Because this is quite a dusty operation, I'm going to be wearing a mask. This is the tool I should be using. It's a little bench grinder, but it's got an attachment for a power tool, so I can put I've got a little wire brush in there now, and I can put little abrasive wheels in there to clean the ports up afterwards. It's a little bit noisy, so I shan't be doing much talking while I'm doing this. The first thing I'm going to do is put a mask on because it is quite dusty and I don't really want to be breathing in the carbon dust and the aluminium dust. It's quite unpleasant. Right, here we go. Right, so you can see a little bit clearer there what I'm doing. So if I just tilt the head a bit towards you so you can see a bit clearer what's going on. Hopefully the light isn't glaring too much off that surface for you. So all I'm doing is just removing the carbon off the surface of the combustion chamber first, before I start removing any metal. I've had a little go here with the abrasive pads and it cleans it really nicely. This wire brush just gets rid of the carbon. You might just be able to see the puffs of carbon coming up off the brush there. Ordinarily I would have a vacuum cleaner running to suck up the dirt, but that is very noisy and you wouldn't be able to hear what I was saying. This is noisy enough for doing the video work. I can't be videoing all of the work that I'm doing here. I'll give you little bursts of it to show you what I'm doing, but there's probably going to be 40 to 60 hours worth of work in preparing this head, which makes for pretty boring viewing. So I'll just give you some little snippets as I go along, so you can see what the process is. I've got a fair bit out of that one. Still a bit more to come out. The carbon dust breaks up into a very, very fine powder. It's soot, basically. If you've ever seen anybody cleaning a chimney for an open fire or a log burner, the soot is very, very fine powder and it gets everywhere. It's very easily breathed in. It's very unpleasant if it gets in your lungs. At the very least it'll make you cough. At the worst it can make you very ill. and it goes everywhere. It will cover everything very quickly, so I will be using the vacuum cleaner to remove the dust as I go, just for dust extraction. As I say, the vacuum cleaner is very noisy combined with this machine, so there we have it. So I'll continue with this. I suggest you pop down the workshop with the other Dave and he'll show you how to do some measuring of the cylinder bores and the crankshaft. In the meantime, I'll crack on with this and I'll see you back here probably in a couple of weeks. And just like that, I'm in the workshop. So we'll leave old Dave mucking about in the shed, grinding and fettling, and we're going to do some measurements on the cylinder block. If I just rearrange the camera slightly so that you can see what we're doing. I built this engine in 2017. It's a 1 mil overboard block, giving a total capacity of 1884 cc. So that's just over 40 cc more than the standard 1839. Using high compression 12:1 forged Wassenaar pistons and forged steel rods and the standard MX5 VVT forged steel crank with ACL race bearings, ARP fasteners, all of the good bits. Unfortunately, I was remiss in my choice of oil, and it was too light a grade of oil, didn't have sufficient film strength for the pressures generated by this high compression larger bore engine, and consequently it took out the big end of number 2 cylinder, spun the bearings on the crank and damaged the crank. So we'll have a look at that as well a bit later on, but for now, before I rebuild this engine, I just want to make sure that the bores are good, they haven't worn. In truth, this engine has only actually done probably 40 or 50 miles since it was rebuilt, so there should be no measurable wear in the bores. There's some very light longitudinal scoring, which is so light that it will hone out very easily. You can't feel it with a fingernail, you can just see them, so they're not a problem. A light hone will clean those up, and I will be rechecking the bore diameters after I've honed it, but for now I'm just going to go through the process of measuring the bore diameters in the block. So I'll reposition the camera and then you can see a bit better what I'm doing. Right, so this is the cylinder block. It was rebored 1 mil over bore. That gives it a bore diameter of 84 millimeters. So I just want to double check that they are correct, and we'll take it from there. Now I've got two methods of measuring. I have a dial bore gauge, and I have an internal micrometer. The internal micrometer is very good. It's an absolute measurement, so you can read off directly the diameter of the cylinder from that. The bore gauge is a relative measurement, if you like. It's a comparator. We take a 75 to 100 micrometer, and first thing we do is check that that is accurate. So with its test piece in, so there, you should just about be able to see that is on 0. That's a 75 mil test piece, so that micrometer is accurate. Right, so once I've checked the micrometer is accurate, I then set that to read 84. So we've got 80, 1, 2, 3, 4. Set that onto the 0 and lock that off. That is now set at 84 millimeters dead between those 2 points. And now I can take the bore gauge, pop that between there, and a little bit fiddly. So when it's on 84 mil, the gauge is reading 0. On the bottom of the bore gauge. You've got a pair of wheels to run against the edge that you're measuring to. They're spring loaded, and in the centre is a spring loaded pin, and that moves the gauge. So with that dimension fixed and that able to move, we can read off a relative dimension. So if I pop that into the bore, these are 0.01 millimetre increments, and I'm reading 84.04. Now the beauty of using a bore gauge is that you can just roll it down the bore and check. Because what I want to check is that the cylinders haven't worn oval. There shouldn't be any in the longitudinal direction of the crank, but there may be across the cylinder. If I turn that, and yeah, I'm getting the same. Getting the same readings all the way down in both directions. And again, that one's the same. So basically all I'm doing is just rocking it and watching for the highest reading, the smallest reading, which is there. And then if the 0 point is 84, then each increment is 0.01 of a millimetre. I'm actually getting 84.03. 0.03 of a millimetre. There's 40 thousandths of an inch to a millimetre. So divide 40. Yeah, I can't do the maths in my head. I'll have to check it with the calculator, but it's pretty close. The important thing is that all of the cylinders are the same, and they're the same all the way down and in both planes. And they are. Yeah, so I'm happy with that. All right, we'll just see what that 0.04 equates to. So 40 thou per millimetre times 0.04 equals 1.6 thousandths of an inch. That's so tiny that it's not going to worry me in the slightest. The truth of it is, the company that machined the bores for me took one of the pistons as a sample and made the bore's diameter to match the pistons to give the relevant clearance. So the fact that it's 0.04, 1.6 thou, bigger than the 84mm doesn't bother me in the slightest, because they've matched the bores to the pistons, rather than just blindly going and saying 84mm. So the 1.6 thousandths of an inch bigger is there for a reason. It's intended that way. It's not a mistake. So that's the bores checked. They're all good. The other thing I want to do this morning is check the new crank that I've got. It's obviously not a brand new crank, it's a second-hand, another crank. So I'll get the decks cleared, we'll get the crank over here. I'll show you what happened to the old crank, and then we'll get the new crank up and take some measurements. So here we have the old crank. This is the big end that got taken out. As you can see, the surface is pretty rough all the way around. I've just got it sitting on a couple of stands that I made up with a couple of bearings so that I can easily rotate it to check everything. So I've got a data sheet for the ACL race bearings that I'm using, and this gives me the minimum dimensions for the main and big end journals, and for the big ends conrod journals the minimum dimension is 44.94 millimeters. That's the minimum. Maximum is 44.956, so we've got 0.016 millimeters tolerance between minimum and maximum diameters. The big ends, the main bearings, these are the ones that the crank rotates in. The conrod bearings are the ones that rotate in the conrods and push the pistons up and down. The main bearings have a minimum shaft diameter of 49.938 and a maximum of 49.956. So I've got a 25 to 50 micrometer now, and again, first thing we'll do is check it for true, for zero, with the 25mm spacer, and as you can see, that is on zero. It's the 25mm test piece. So I've zeroed my micrometer, checked it's accurate. So each full turn of the barrel is 0.5 millimeter. So we're looking to measure 44.94 to 44.956. So that would be 45, that would be 44.95, and then those increments in between. So place that around the journal, just adjust it, very light finger pressure. Use the ratchet if you want to. That's a nice sliding fit. 44.94. So that's spot on minimum. I'll take the other measurement on this side, and that's exactly the same. Turn it 90 degrees. Measuring big end journals can be a bit tricky because you've got to work in between the webs, and that's the same. And yeah, that's the same. Right, so number one was okay. Number two is where the damage was done. So let's see how much damage we inflicted. Turn it that way, be easier to get to. .9, 44.9.04 below minimum. So that's quite a big chunk of metal that got taken off that one. Check it that way and see what we've got. Because obviously when they're worn, they don't wear necessarily evenly all the way around. Yeah, 44.838. So it's properly knackered. I'm not going to bother measuring the other journals on this crank because it's shot. That one, I could have it reground and use undersized shells. I never know quite whether to describe them as oversize or undersize. They're over thickness to take up the difference, so if you had that ground you'd probably need to have 1/10 thou taken off it, 10,000ths of an inch. You would use bearing shells that are 1/10 thou thicker to take up that extra meat that's been taken off. So let's pop that one to one side and get the new crank. I'm using the term loosely because it's not brand new. It's a pre-loved one. So let's measure this one and see what we got. .94, which is perfect, absolutely on tolerance. .94, that's great. Right. .94, so that's wonderful. The big ends are all bang on minimal tolerance, which is grand, and the mains are 49.938 is the minimum. .938. So that is all good to go. That crank doesn't need anything more than cleaning. So that's about it. We'll pop back to the shed and see how old Dave's getting on with cleaning that cylinder head up. Right, well that's all loose carbon removed from the combustion chambers and the inlet and exhaust ports. So now I shall change the wire brush for a drum sander on there, and we'll start cleaning up the ports themselves. I'm not looking to remove huge amounts of metal because they don't need it. The cross-sectional area of the ports is pretty good. What I need to do is remove the rough surface in the ports to improve the airflow. The airflow is very important in getting air into the cylinder and out of the cylinder. Basically, an internal combustion engine is an air pump. The greater the volume of air that it can flow or transfer in each revolution, the greater its volumetric efficiency, and the volumetric efficiency is directly proportional to the power that the engine will produce. So what we want is a clean and smooth entry of air into the cylinders and a clean and smooth exit of exhaust gases out of the cylinders after the combustion. Any roughness on the surface in the ports will cause the air to tumble and swirl at the edges of the, if you imagine it as a tube of air. So the air in the centre will be moving quite rapidly and smoothly, but the air along the edges will be interrupted by the roughness of the surface, and it will create swirl and tumble in the air, and it will actually restrict how much air can go into the cylinders because it's swirling around in the ports rather than going straight in. So all I actually want to do is smooth out the surfaces of the ports. Now there used to be a train of thought that ultra smooth polished ports were detrimental in that droplets of fuel could condense on the cold surface, and therefore you wouldn't get smooth and efficient fueling, particularly at low RPM and when the engine was cold. The reality is that the engine warms up pretty quickly. The Mazda engines, in my experience, these engines come up from stone cold, say 10 degrees, up to operating temperature of 80 degrees in about 10 minutes. 15 minutes idling. So a little bit of fuel condensation at low speed, low temperature is not actually a problem for them. Once it's up to temperature, of course, the fuel can't condense on the walls of the port because they're warm. It condenses on cold, not hot. So that's the next step, is to start cleaning these up. I'll pull the camera down and show you a close-up of the ports and show you some of the issues that I need to address. Okay, so that's looking into the inlet ports from the cylinder head side, from the combustion chamber side. I can lay that torch like so. Now you can see here we have a step all the way around, and it's quite a pronounced step there. This portion is where the valve is said to be shrouded. That might give better illumination of it. My spotlights aren't working at the moment, so I'm having to just use a torch for close-up lighting. So you can see there's quite a step, and the valve, that quadrant of the valve is quite close to the edge of the combustion chamber. Likewise over on this valve it's exactly the same, so we've got quite a sharp step and it's quite close to the edge of the combustion chamber there, quite heavily shrouded. And the cylinder edge is there, and that sharp edge isn't helpful because that produces a shelf. So when the piston comes up and compresses, the air in this area is forced in towards the centre of the cylinder over that sharp edge, which again causes turbulence. Now inside the combustion chamber, turbulence isn't such a bad thing because it helps to keep the fuel and air mixed properly. You can see that is the spark plug hole, so the spark plug would be standing just proud in there, and you can see there's a little, almost like a little ski jump there and there, and the purpose of that is to direct the air and fuel mixture up towards the point of the spark plug where the spark happens to ignite it. Without that you don't get quite such clean combustion. On the exhaust ports, much the same story. There's a bit of a step there and in the corners. Now the exhaust ports aren't quite as badly shrouded as the inlets, so they don't need quite as much work. And the down inside the exhaust ports is just a bit of a rough surface. It's not too bad. There's a slight step from the valve seat. On the inlet ports there is quite a pronounced step. So there, it's quite a pronounced step where the pocket for the seat has been machined out, and it's been machined in part way down into the port, but where they've stopped it's just left a ridge.